Today I want to try a style of video where I pretend like I'm teaching to a class, specific class, like say preparing for a final, and this is a review session for the final, say. And the class I have in mind for this one is Math 55. So Harvard has this class called Math 55, which has become rather well known recently due to some social media hype. And there's a whole Wikipedia page on this. And to give a brief summary on what Math 55 is, it's for a freshman class, so for the first year math classes at Harvard, it's the most accelerated one, requiring most, say, mathematical maturity. And roughly the topics it covers, so I can give you a bit of a quick insight. So 55 is divided into 55A and 55B. 55A in the fall semester and 55B in the spring semester. And 55A essentially covers the material from Math 25A and Math 122 at Harvard. So Math 25A is, I suppose, like the second most accelerated class for a freshman at Harvard. And this is by no means an easy class in its own right. So this is a class that covers the usual theoretical linear algebra. So I guess in many colleges, this would be like a second semester linear algebra that if you're not, say, going to like a top school, then maybe this is only covered in third or fourth year. So this is a linear algebra that's not really geared toward engineers, but maybe more for like pure mathematics-oriented people, where, say, the focus is not necessarily on like computational things like matrices or like row reduction, QR decomposition or things like that, but maybe it's more towards like the abstraction. And like you learn about things like generalized eigenspaces, and determinant is going to be a multilinear alternating form that where identity gets sent to 1, for example. So that's one class. And Math 122, on the other hand, is a standard first semester, say like group theory class. And what exact material 122 covers at Harvard depends on which professor is teaching. But I think it's safe to say that roughly first, say 1 through 5 chapters of Dummy 10 Foot is going to be covered. So the usual things like the quotient groups, CLO theorems, like fundamental theorem of finally generated abelian groups, like all of that's thrown in there. Whereas in 55B, this I think depends a little more on the professor in the recent years, but roughly speaking, it's going to cover 25B, Math 113, and it's going to cover Math 131 at Harvard. So it's possible that maybe the numbering changed, but I think, at least going by my memory, it's these three. So 25B is the second semester version of 25A, and this is covering the usual real analysis. And importantly, not just single variable, but also multivariable. So for the single variable, maybe it's like first 7 chapters of baby root-in, and then maybe some multivariate stuff, so you know things like inverse function theorem, like implicit function theorem as well. But I guess it's important to point out sometimes 25B is rather slighted in 55B, and sometimes like you kind of assume people are kind of familiar with basic real analysis, and I guess to some extent, real analysis, a lot of it, once you know like sufficient points at topology, there isn't too much content on top that you have to know when it comes to differentiation and integration. Really, the things like uniform convergence is key, and that certainly is required for 55B, and that's always covered, I think. But the two that 55B does emphasize are going to be 113, which is going to be complex analysis. This is, again, the standard first semester undergraduate complex analysis class. I mean, there are many excellent books on this topic. Like, my favorite is probably Stein and Shakarchi Volume 2, but Ahlfors complex analysis is another widely used one. 131 here is going to be, like, it's roughly going to be the material in Moncrief's topology, like something that almost every mathematician, I'm sure, knows. So this is going to be a standard basic point set topology. But I don't know how much emphasis there really is on the pathological things. Like, I'm not sure if 55B people can reliably tell you a space that's regular but not normal and things like that. But there's a little more algebraic topology as well, mostly just on pi 1. So mostly things like fundamental groups and obviously the covering spaces. So you'll be able to use things like, say, Seifert-van Kampen theorem and like the usual equivalence statement between fundamental groups, subgroups of fundamental groups, and certain specific types of covering spaces. So this is roughly what Math 55 covers. And in fact, this is coming straight from the source, because as an undergrad at Harvard during my time, I actually gave multiple sections and final review sessions for Math 55. So I know there's a lot of misinformation of 55 floating out there, but in some sense, this video is coming straight from the source. And I just want to, I don't think I can exactly recreate the review sessions because it's been some time and the lecture notes has not been preserved as far as I know. Maybe I should have asked one of the students if they have a copy. But today, I just want to focus mainly on the Math 113 part of Math 55B session, which is going to be the complex analysis. So my goal is to present, say, like, to someone who's taken 55B, but even if you've never taken 55B, I think you can still gain some things from this. It's not going to be fully self-contained because mostly I'm going to assume like a little bit of things about 131 as well, since that usually is an assumption if you're presenting to 55 students. But even if you've never taken it before, you can still get some interesting insights and at least get some basic feel for what first year complex analysis and what the very prepared, say, Harvard students get to take their freshman year. It's important to add before I go on that certainly the material I'm going to present is not going to be something revolutionary. It's obviously I'm heavily relying on the references that I've read and like seen from other professors in the past. So it's going to be many textbooks and many lectures in my experience that's really going to combine and synthesize together in this session. So I'll give you some list of references down in the description. But despite the wealth of written references, I think these sort of like lecture references where it's like a fast-paced, high-quality lecture on, say, like 55 topic, I don't think these are quite as prevalent. So hopefully this gives a bit of a contribution in that regard. It's possible that there are already many videos like this out there and I'm just not aware, but I do hope the storytelling here that I'm about to spend maybe, I don't know how long this video is going to be, maybe 90 minutes on, is going to benefit at least one person in the future. Maybe a future 55er at Harvard, who knows. Okay, I think that's enough of a prelude. I do want to get started right away. So again, I'll be mostly just focusing on the complex analysis part. And actually, right before we get started, let me just mention one more thing that I think forgot to add here for 55A, that some very basic representation theory of finite groups, not Lie groups, is covered as well. I think Michael Artin's algebra has an excellent chapter on this that gives you enough insights for what you need for 55A for this. Okay, so let's get started. To begin with, I want to open with one of my favorite examples, and that's on finding the radius of convergence of 1 over e to the x plus 1. So to be more precise, I'm talking about the radius of convergence of a power series, and here at x equals to 0. So if I look at a power series expansion at x equals to 0 of this function, then what is the radius of convergence of this? And the one way of trying to approach this is by looking at, like, say, function 1 over x plus 1. Now, if you look at 1 over x plus 1, it's very well known. This is standard like calculus 2 in the United States. Here, the radius of convergence is 1. And one way of getting an insight on this is that if you look at the real line, so this is, say, 0, this is 1, this is 2, this is minus 1, this is minus 2. And when you look at 1 over x plus 1, 1 over x plus 1 is an extremely well-behaved function as long as you're not at this minus 1. At this minus 1, you have a denominator becoming 0, and near minus 1, everything is blowing up, right? So you have a problem at minus 1. So if you're, so again, here when I say radius of convergence, I'm centering it at x equals to 0. So when you're looking at this from the point of view of x equals to 0, the largest radius where you can, about x equals to 0, that you can expand to before you hit one of these like singularities where you have a blow up is r equals to 1, right? The maximum distance you can go is r equals to 1. And that's one way of thinking about the radius of convergence. But obviously, 1 over e to the x plus 1, this is always defined on the real line. E to the x plus 1, I mean, this is never 0. I mean, it's always positive, greater than 1. So how can there be any problem? And the problem, miraculously, arises when you not just look at the real line, but you look at this in the complex plane, right? So let's say you look at a complex plane where this is the real axis and this is the imaginary axis. And a very well-known formula is that e to the pi I plus 1 is equal to 0, right? So when x is equal to pi I here, then you actually have this sort of blow up happening. And that's happening, say, here at pi I. And in fact, this turns out to be the closest to 0 singularity. So if you're looking at it from the point of view of x equals to 0, or x equals to 0, And in fact, you can define e to the x plus 1 where x is like any complex number. This is one of the basic things in complex analysis. Then the closest singularity is the distance pi away. And here the radius of convergence, in fact, turns out to be pi. And I think this is just one of many insightful examples that shows that what's happening in the real line is really a shadow of what's happening in a one dimension higher in the complex numbers with all the algebraic multiplication defined using I squared equals to minus 1. So complex numbers, thinking of them as some imaginary strange construct is not the right viewpoint, but the correct viewpoint is complex numbers is where things are nicer, where things are more perfect, and by looking at the behavior of functions in the complex sense, you in fact gain a lot of insights on the real functions as well. So it in fact makes no sense to only know real analysis and not know complex analysis in my opinion. And I think this is a nice example that illustrates this. So the first thing I do want to start with is what is complex differentiation? What is complex differentiation, and how is this fundamentally different from differentiation in the real sense? And to do so, I think it makes sense to do a bit of a divide and think about what does it mean in the sense of differentiation of a function, of some function that's going from R2 to R2. Because in complex differentiation, you're really looking at a function that's going from C to C. And complex plane can really be identified with a two-dimensional grid, right? But obviously, in two-dimensional grid, where this is like x comma y, like you're thinking about it as x plus iy in complex sense. And I guess like here the multiplication structure is given by I squared equals minus 1, and maybe here like you don't have as natural a priori like multiplication structure in R2 to R2. And the way you define differentiation here is just by saying that f can be approximated using a linear map from R2 to R2, so a 2x2 matrix, if you pick a basis, up to like some like sublinear the remainder term. To be more precise, if you want to be differentiable, at some x naught comma y naught, this really means that if I look at f evaluated at a vector x naught plus, so say some delta x and y naught plus delta y, then this is f evaluated at x naught y naught plus the derivative, and derivative is really just some linear transformation where you're plugging in delta x and delta y. You can think of this as being a 2 vector in R2, and this linear transformation, this is just a 2x2, this is a 2x2 matrix, essentially. And then there's a remainder term where, I mean, you have some sublinearity here. So where if you look at, say, like R of delta x, delta y, and you divide by the lengths of this delta x, delta y vector, then when you take the limit as like this delta x, delta y norm goes to 0, then this entire thing goes to 0 as well. For a beginner's point of view, complex differentiation is defined in exactly the same way, right? So here when I say you're differentiable as say like C naught, what this means is that you have some behavior like this, f of z plus delta z is equal to f of z plus f prime of z delta z plus some remainder term. So here you're kind of thinking of f prime of z, this multiplication by f prime of z, as being a 1x1 matrix, right? A 1x1 complex matrix. So this is a number in C. That's performing the only possible linear transformation, which is the scaling, right, to this delta z vector. And we again have the sublinearity, right, where this part is a little o of, like, say, normal delta z. And despite like this similarity, it's important to realize that here like things are fundamentally different than differentiation from R2 to R2. And one way to see this is to really think about what complex multiplication is doing, right? And I guess since I'm using C naught here, let me make the notation consistent and put all the C naughts here as well. And what I'm about to say is when you multiply by a complex number, so let's look at f prime of C naught, this can be written as say R times e to the I data, right? And multiplication, complex multiplication by some real constant, this is just doing dilation. And multiplying by e to the I data is doing rotation by data in this case. So here, when you multiply, I'm dilating and I'm rotating. In particular, the orientation of the space is staying the same. In the sense that, like, if I'm rotating clockwise in the input space, then in the output space, since I'm just rotating and dilating, you should also be rotating clockwise for the output, for example. So this is telling you that, I mean, say like a very basic example of Z mapping to the conjugate of Z, which seems like, I mean, it's one of the most basic complex function, right? This is just going from like x plus iy mapping to x minus iy. This is not differentiable. This is not differentiable in complex sense. Exactly because when you're mapping from x plus iy to x minus iy, so if this is the input space, and you have the output space, which is also C, then say like rotating this way, like this gets reversed, right? This gets reversed to rotating this way. And if you're complex differentiable, then you have to be like locally multiplying by a complex number, which needs to preserve this like rotation direction. So this is not complex differentiable, whereas it is certainly differentiable as a map from R2 to R2. I mean, this is a linear map, right? This is this is just a reflection from the point of view of R2. So in this case, the remainder is 0 even, right? This is as differentiable as you can be in R2 to R2, but it is not complex differentiable. So this already shows some rigidity that's inherent in the complex functions, and this leads right to what's called the Cauchy-Riemann equations, which says the following. So if I have a function from like C to C, then you're essentially mapping Z to say like U of Z plus I times V of Z, where like this part is going to be real and this part is going to be real, right? So you can break down a complex valued function into real part function and the imaginary part function. And if you like, I mean, you can think of this Z as like x comma y, or more precisely x plus iy. So U of Z is really U of say like x comma y, and V of Z is V of x comma y. So U and V can be thought of as functions from R2 to R. And since locally what's happening is you're multiplying by a complex number. When you look at the Jacobian of this function, so this is a map from C to C, but you can also think of this as a map from R2, so x comma y, mapping to U of x comma y, V of x comma y. So you can also think of it as a map from R2 to R2, just with more structure, given by like complex structure, right? So locally speaking, when you look at the Jacobian of this map, then you need to look like a rotation map. So you should look like a rotation matrix. And I mean, it's a rather basic result, say from 25A, 55A. The rotation matrix, I mean, looks up to, when I just, without lots of generality, just let scaling be 1, it looks like something like this: cosine data, sine data, and this should be orthogonal. So sine data, minus sine data, cosine data. So rotation matrix has this form where these two diagonal entries are the same, whereas these two diagonal entries are negatives of each other. And because of this, and because when you look at the Jacobian of this map from R2 to R2, I mean, this is basic real analysis, that this is going to be du dx, this is going to be dv dx, right? This is going to be the x movement term, and you're going to have du dy, dv dy, and based on this intuition, we would expect these two entries to be the same, and these two entries to be negatives. And that's exactly what you get. That's in fact exactly what you get. And what Cauchy-Riemann equations states is that if f from C to C, if this is complex differentiable, then what we in fact get is that du dx is equal to dv dy, and du dy is equal to minus dv dx. The converse of this is true as well. So maybe an interesting note on the converse, it's actually quite easy to prove. I think it's just basic Taylor series remainder sort of theorem, that if the Cauchy-Riemann equations is true, and then everything is C1, right? If all of these are continuous, all of these partials are continuous, then you in fact have holomorphic, which is just a fancy way of saying complex differentiable at every point in the domain. I'll make another note on the domain pretty soon, but it is in fact true that if I'm remembering this correct, I think there's a University of Chicago first year graduate complex analysis book that has a proof on this. I don't think it's easy. That if it's Cauchy-Riemann plus just differentiable in the real sense, like it's actually sufficient. That this is actually sufficient to get holomorphic. This is just an interesting note I want to make before I move on. There are more things I can talk about when it comes to Cauchy-Riemann, like some basic facts, like real part of holomorphic function turns out to be harmonic due to this. But for now, I do want to skip ahead and talk about the very important, in some sense, like one of the fundamental cornerstones to first semester complex analysis, which is the equivalence between analytic and holomorphicity. So let's get to that. So a key result that I want to at least give some intuition for is the result that holomorphic And let me actually separate things out once again. Holomorphic and analytic magically turn out to be the same for complex functions. So before we get started, I just want to talk about what kind of functions we're considering here exactly. So I'm thinking about functions from like U to C, where U here is a subset of complex numbers, and I'm going to call this a domain. I think Stein and Shakarchi might use this term. And by domain, I really mean an open and connected subset here. It's a rather basic fact that open and connected subset of a Euclidean space is going to also be path connected, right? So you don't have weird pathological things going on here. I mean, the proof of this is just basic point set topology. I'm not going to do it here. Just consider any path connected component and show it's open and closed. I think a lot of 55ers should be able to prove it just from that. So having said that, let's first talk about what is holomorphic, just a little more precisely. So what this holomorphic means, like, all I mean by this is that f is differentiable in complex sense, right? At every z in U, at every point in this domain. So this is in some sense a very basic just differentiability statement. On the other hand, analytic is really a statement about power series expansion existing and equaling the function. So I mean, just to draw it out, so you have some U being open subset of C here, and no matter what x naught, or I guess C naught in this case, since we're complex, C naught I pick in U, what we have is a positive radius of convergence, and it's a key here that it's positive, non-zero. So we have some sort of disk that looks like this, right? With say radius r, and here radius is greater than 0, such that no matter what number I pick within this ball of radius r, centered at C naught, I'm just using this notation for the open ball of radius r centered at C naught. What we have is we have some expansion f of z is equal to a naught plus a1z, z minus c naught, plus a2 times z minus c naught squared. So we have this power series. Of course, the a naught, a1, a2 here are uniform for all the points within this ball. And the key thing is we have this equality, and here the radius is actually greater than 0. So it's not. It is true locally around C naught, even slightly away from C naught. And for analytic functions, a lot of the usual real analysis proofs just carries through. I mean, there are many well-known facts. I mean, like for example, here the radius of convergence of like a power series of this form, is going to be like lim sup as n goes to infinity of, I think it's like a sub n to 1 over n, and then you raise it to -1, right? Where infinity to -1 is 0, and the usual things like that. But a key fact, really from real analysis, since the proof is basically the same, is that within this open disk of convergence, if you are an analytic function, you can actually differentiate term by term. So you can f prime of z is what you expect. You can just differentiate term by term here in the infinite sum. And you can do this infinitely within this open disk of convergence. All the derivatives converge in this open disk of convergence as well. So you can differentiate infinitely term by term. And now the cornerstone result is that these two are actually the same. For complex functions. And this is mind-blowing in some sense, because I mean, think about what I'm saying here. I'm saying if you're differentiable once, you turn out to be analytic, which we know to be able to differentiate infinitely many times. So what I'm saying here is differentiability once in complex sense implies differentiability forever. So that's one implication. Another implication is like any differentiable real function actually has like this sort of Taylor series expansion that is valid in a non-zero, in a non-trivial region around the point. Like, I mean, for example, I mean, let's think about counterexample to both of the claims I made. Like in the real world, right? If you're only talking about real functions, I mean, it's well known that you have a function from R to R that is like differentiable nowhere differentiable. I think it's how people usually say it, but it is everywhere continuous. There are many standard ways of constructing this, like something like a Brownian motion path, I think, almost surely is one example. But given this, I mean, if you look at the integral from like 0 to t, and you're mapping like something like this is a function that's differentiable once, right? This function will be differentiable once by fundamental theorem, but it will be nowhere twice differentiable, for example. So in the real sense, like this is certainly not true. And another famous counterexample for real numbers is if you think about a function, define something like this, where it's e to the -1 over x squared for x away from 0, and say 0 for x equals to 0. So this is a function where you have like a pretty severe exponential decay towards 0 near x equals to 0. And because of that, since you're decaying so quickly at x equals to 0, you can check. So I encourage you to check this. You can check that no matter how many times I differentiate this at x equals to 0, you get 0. So for all n greater than or equal to 0, the nth derivative of f evaluated at 0 is 0. So because of this, the Taylor series expansion at 0 is actually 0 plus 0x plus 0x squared plus 0x cubed, and this clearly has radius of convergence 0. Despite the fact that this function is C infinity, this is a C infinity function, it's smooth, like you can differentiate it infinitely many times, but you do not have Taylor series expansion that's non-trivial. So in the real world, you have all of these counterexamples. But what I'm saying is, like in the complex world, you don't have anything like this. Everything is perfect. So let's think a little more about what the implication is actually before we go even further. And I think one pretty important implication is given by this pretty basic fact analytic function that's I think still like kind of quite nice and surprising, is that if you have a function f from say u to c that's like complex analytic, and it has a limit point of zeros. So what I mean by this is, like, for example, you have something like this where you have u, and then you have some zeros, say like c1, c2, g3, g4, g5, g6. So where f of cn is equal to 0 for all n. And these are actually converging to some point, say like c naught, where cn is converging to some c naught in u. In this case, so if you're analytic and you have like these sort of clustering of zeros of the function, I mean, trivially, maybe another possibility is maybe you just vanish on like some segment. If you vanish on some segment, there will be like a stronger condition, for example. And in this case, the claim is that f is actually identically 0. F is 0 everywhere in U. And this is just a fact about analytic functions in C. And the proof is not hard, so I want to sketch it quickly. First of all, since you're analytic, you know there is some disk around the C naught. So you know there is some disk here where we do have a power series expansion. So f of z is equal to, say, like a naught plus a1z minus c naught plus a2z minus c naught squared, and so on. And here, critically, because I mean f is continuous, for example, it is analytic. It's like infinitely differentiable even. So we know this a naught is equal to 0 because f at c naught is equal to 0. And so the two possibility here. So the two possibility here is at least in this disk. So let's give this disk a name. Say it's D. So at least on D, two things can happen. Either f is identically 0 on D. So that's one possibility. In this case, I'll continue the argument later. The second case where we're going to get a contradiction is f is not identically 0 on D. And in that case, at least one coefficient here has to be non-zero. Like maybe a1 is non-zero, a2 is non-zero. So just consider the smallest possible coefficient, and we can write f of z in that case as, say, like c minus c naught to some power n times, say, an plus 1 c minus c naught, and continued, right? And here the critical thing is by minimality of n here, this part is non-zero. But now let's think of what happens for some z in D that's not c naught, right? If you're in D and you're not equal to c naught, then this is non-zero. If z minus c naught, if the distance between z minus c naught is small enough, then all of this part, since all of this part is approaching 0 as z approaches c naught, all of this part is going to be pretty close to 0, whereas this is some constant non-zero distance away from 0. So if this is small enough, assuming this is small enough, this entire part is going to be non-zero as well, because you're adding a non-zero thing to something that's like extremely small, right? It's smaller than an in magnitude, say. So what we get here is that everything within this disk, other than a c naught, cannot be evaluated to 0 when you apply f. But we know like c naught is a limit point of zeros, so that cannot be true. So you actually get a contradiction in the second case. So the first case has to be true. So we actually know that there is some vanishing disk here, but we want something actually global. And how we extend this is by using some connectivity argument. It's as follows. So let's consider of all elements in U, where there exists like some disk, right? Like say dr of z, where like here r is greater than 0. Where on this disk f is identically 0, right? Now, there are a couple of things to be pointed out here. From the argument that we just made, this is non-empty, clearly, right? Like C naught is one example of a member of the set. And another key thing to realize is that this has to be closed. And the reason it's closed is really a repeat of the same argument we just made. If you have a limit point of elements of the set, that's in particular a limit point of zeros of f. So the limiting point that we actually care about should also have this property by the argument that I literally just sketched out here. And it's also quite obvious that it's open, because clearly, like this entire set is a union of sets like this, which is open. Because any member of this DRZ has the same property that we claim here. So because U is a domain and is connected, this actually has to be equal to U. So we're done. So that proves this on U. So let's think about some implication here. So what are we saying here? So since analytic function has this property, and again, I haven't established this, but if you believe me for a second that holomorphic and analytic are the same, what I'm saying here is if you have a differentiable function in complex sense, if you're holomorphic, and you vanish on a segment, like there's a tiny segment in the complex plane where all of this gets sent to 0 by f, then what I'm telling you is f is a zero function. So again, this is highlighting the rigidity of the holomorphic mapping, right? The fact that you vanish on a segment implies you vanish everywhere in the domain, even like far outside the segment, is quite remarkable. So again, this is not true at all for real functions. You can certainly imagine functions. I mean, these are well known in like say like partition of unity sort of argument, where like you are at 0 and then you rise smoothly away, where like you're actually infinitely differentiable. So this is actually true for real functions from R to R, but this is again not true for complex functions. So how do you establish this equivalence of analytic and holomorphic? Well, I mean, it really the basic real analytic proof, I mean, it really implies holomorphic. This is like a more basic fact. I mean, it really comes from this one. I didn't prove this either, but again, like if you look at like say baby root in chapter 7 and you look at the proof there, like the same proof is going to work for a complex valued function. I think the more complex nature, really more fundamental one might be this direction. How do you go from holomorphic to analytic? And the detour that we're going to take to get this, not really a detour because it's still going to be a lot of fundamental things, but how we're going to get this is by the way of Cauchy integral formula. And it's going to take maybe a little bit of time to get here. I just want to provide some intuition. We're not necessarily going to be rigorous for the purpose of this review session, clearly. So the first thing I want to remind you is like the concept of an integral, a path integral in the complex plane. So if I'm say like moving from here to here, and you can think of parameterizing this path, so all of this is happening in C, from like time equals to 0 to time equals to 1, then the integral of some function, so again f here can be a function from some domain to C, and let's assume, I guess, here this entire path is actually contained in U. And we define, if we call this path gamma, the integral of f of z dz over this gamma to be just the integral from 0 to 1 here of f of gamma of t, like gamma prime of t dt. So this is the dz, and this is gamma is how you parameterize the c as you move in the gamma. And of course, like there are some things to check, like this is well defined up to like maybe if you're speeding up here and then you're slowing down here, like you want to make sure that if I'm using slightly different path, like this integral is, we still have the equality here, so everything is consistent. But none of these are too hard to show. And once you have this defined, and I guess like I also mentioned here, for the purpose of this presentation, we're not going to deal with like pathological gammas, like maybe like space filling curves or things like that. We're only going to really focus mostly on things like circular gamma, or the ones that are like piecewise it just looks like a line, for example. So we'll just take the approach of say Stein and Shakarchi and not worry about a lot of pathology here. So with that point out of the way, one slightly more basic result than Cauchy integral formula that's still like remarkable is what's famously known as Cauchy's theorem. And what it says is the following: if I have some domain U, and here I'll assume U is simply connected, like in the language of topology, I mean this means like pi 1 of U is equal to 0. Like in a more informal sense, I'm saying U doesn't really have any holes or things like that. So every path that I can draw So if you have a hole and you have a path, you really cannot contract this path continuously to a point, right? Because this hole gets in the way. Whereas if the hole was not there, then you can imagine this path can be shrunken down like continuously until you just have a single point. So that's what I mean by simply connected. You don't have any obstruction to these paths like continuously deforming down to a point, and that really means the fundamental group is 0, as you know from like topology part of 55. And what Cauchy's theorem says is if I have a simply connected domain and then I consider some path like path gamma here, and you look at the integral of gamma of f of z dz, then you actually get 0. You actually get 0. So when I integrate, and I guess, sorry, here the key thing is this gamma is a loop. Like the start point and end point is the same. So if I loop around in a simply connected space and I integrate around that loop of any f here, which is like holomorphic, any holomorphic f, then what we in fact get is the integral is 0. So this is Cauchy's theorem. I mean, there are standard proofs you can find in Ahlfors and Stein and Shakarchi. I think they use like Gorsat's method. But we're not going to do that, and the intuition I'm going to present instead is the one I think I saw in Needham's visual complex analysis, and I think it's one of just the nicest intuition to have in mind. The intuition is essentially that this remarkable effect is really coming from the fact that complex functions locally looks like a rotation, along with some dilation. I mean, say your gamma looks something like this. Your gamma looks something like this. I mean, what you can do is you can break up this gamma. You can break up this gamma into like small like local parts. So like for example, I can break this up into like say like this loop, one loop that goes like this, and then I can have another loop that, let's just make sure we traverse in the opposite direction, like this, and then like this. So we first go this way, and then you continue doing that. You continue doing that to split up gamma into a composition, not composition, but a concatenation of multiple different loops, where I just ensure that wherever you intersect, where the two loops intersect, you're just moving in the opposite direction. And now what you can realize is if I call this purple path gamma 1, this orange path gamma 2, and so on, the integral along gamma is really the same as integral along gamma 1 plus integral along gamma 2, and so on. And the reason this is true is because the integral in this intersection parts are canceling out. For one integral you're moving in one direction, for the other integral you're moving in the opposite direction. So they're negatives of each other. So those are parts that are canceling out. So really this large integral can be broken down into smaller, more local paths. So let's just focus on a single one of this gamma n, which I'm just going to, in the Möbius notation, also call gamma. And let's say it looks more like a rectangular path. So let's say your gamma looks something like this. And I want to show here that, so this gamma is really one of these smaller integrals, but I want to show that here integral of gamma of f of z dz is 0. Well, what does f do? So this is the input space. And when I apply f is locally, because I'm zooming in here, it's going to be a dilation and rotation. So this is going to preserve the orientation, and now we're going to get in the output space the image of gamma that looks something like this. And let's pick 4 points here. Let's call this point A, let's call this point B, let's call this point C, let's call this point D. And intuitively, we're going to have something like, maybe this is like f of A, this is going to be f of B, this is going to be f of C, and this is going to be f of D. And now what is the integral? And now what is the integral of f of z dz on this local gamma? I mean, if we use like some sort of like Riemann sum approximation here, like on this path A, your value of the function on this path A is approximately f of A, right? On this path, because the path is really small here, is really short here, you can approximate the function value by f of A. So here the f of z part looks like f of A, and the dz part, how much you're moving in the complex sense. I mean, let's give this length a name. Let's say this is epsilon. So here, like when you're moving B, you're moving plus epsilon. When you're moving C, you're moving plus I epsilon. When you're moving along D here, or you're moving along the side that contains the point D, you're moving minus epsilon. And when you're going down A, you're moving minus I times epsilon. So the dz part is going to be f of A times minus I epsilon. And similarly, when I integrate along the side that contains B, you're going to get f of b times plus epsilon, and then you're going to have f of c times I epsilon plus f of d times minus epsilon. And if I look at the real and imaginary parts here, right, the real part is f of b minus f of d times epsilon, and the imaginary part is f of c minus f of a times epsilon. And now if you look here, let's look at f of c minus f of a. If you look at f of c minus f of a, that's a vector that's going from f of a to f of c right here. And if you look at a vector, f of b minus f of d, that's a vector that's going from f of d to f of b, looking like this. And the key thing here is when I multiply by I, this is really a rotation by 90 degrees, right? 90 degrees rotation counterclockwise. So when I do a 90-degree rotation on this f of c minus f of a vector right here, you're going to get exactly this, which is going to cancel out with this f of b minus f of d. And the reason everything is 90 degrees here is, of course, because things started off 90 degrees here, and f is preserving this like angular relationship, right? F is going just a rotation locally, so we in fact get 0 here. And of course, this approximation gets better and better the smaller you zoom in. And again, like it's quite important that we do have like holomorphic everywhere here. Like you cannot have some hole here, like for example, where like maybe you're not holomorphic all at this point, at this hole, you have some singularity, and then things are blowing up, right? We cannot have that. We just assume everything is actually nice. We just assume everything is nice all around this region. So like this angular conformal preservation is actually there. So this gives you insight into the Cauchy's theorem. And now moving on, I mean, since I mentioned the hole, let's actually try one example where you do not get 0, and in this case you cannot be holomorphic in a simply connected region. And that's a classic one is integral of 1 over c dz along gamma. So here in the complex plane we have a singularity at c equals to 0, and I'm going to consider just rotating. It doesn't have to be radius 1, it can be radius r here, and I'm going to just consider rotating once counterclockwise around the circle, and that's going to be my gamma. And it's a well-known calculation that this is exactly 2 pi I. I mean, the proof is easy. Let me just do this really quickly. So you just parameterize z as r e to the I data, and this gets you dz being r e to the I data I d data, right? So when you plug everything in here, this turns out to be integral from here. Data is rotating from 0 to 2 pi. You're rotating from 0 to 2 pi. Of r e to the I data I d data divided by r e to the I data, and this is 2 pi I clearly. So that's just a fast calculation. We will actually have a lot more to say about an integral like this 1 over c dz later on, and actually maybe it doesn't hurt to give a little more intuition on this now. And it's that, let's say gamma is not just rotating once, but let's say gamma is rotating twice. So if let's consider another gamma, say gamma prime, where now instead of rotating once, you're rotating twice. So something like this. So now this is your gamma. In this case, when you do integral of 1 over c dz, you're going to get 4 pi I. Rather than going from 0 to 2 pi, you're essentially going from 0 to 4 pi. And one of the fundamental theorems when it comes to these sort of path integral in complex plane is that if gamma and gamma prime are homotopic, so if I can continuously deform this path into this path, then the integral of gamma of f of z dz and integral of gamma prime of f of z dz are actually the same. If gammas look nice, I think this is kind of clear. Like for example, if this is what gamma looks like, and maybe this is what, I mean, it's probably not going to be this nice, but if this is what gamma prime looks like, such that one can be continuously deformed into the other one, here the smaller ones can be like deformed, maybe you enlarge it even more until it becomes gamma in a continuous way. Here I guess one like hand wavy argument is you just put a connector between the two paths. And now you consider a path that looks something like this. So you consider a path that looks something like this. So I'll trace it as you see here. Consider a path that looks something like this. And because this part, if you think about how I drew the path as I was like actually going around, it's being traversed once in one way and the other in the opposite way. So if I consider this blue path like gamma tilde, Actually, let me be a little more precise. So let's say this is gamma tilde. I already forgot which way I was rotating, but let's say I was agreeing with gamma here, and then I rotated it in the opposite direction as gamma prime here, and then I continued on rotating like this. In this case, what we see is integral of gamma tilde on this corridor, where when I'm traversing it once in one direction, the other way in the other direction are going to cancel out. So integral of gamma tilde is really integral of gamma minus integral of gamma prime. And the minus sign for gamma prime comes from the fact that gamma prime, at least in this picture, is going counterclockwise, whereas gamma tilde is traversing it clockwise, right? So you get this extra negative sign. And by Cauchy's theorem, this integral is 0. So this gives you an idea why these two integrals are actually the same. So I guess fundamentally what I'm saying here is because of this fact, when I consider like a path that like say winds around, it's not exactly a circle, but let's say this is your gamma. It winds around twice along 0. So this winds around z equals to 0 twice, whatever this means in this rough intuition, then the integral of gamma of 1 over c dz should be exactly the same as for this path, right? Because this path and this path are homotopic. They are really the same element in the fundamental group of the circle, or fundamental group of the complex plane minus the origin. So one insight from this is when you look at 1 over 2 pi I times integral of gamma of 1 over c dz, this really gives you, in fact, it always gives an integer. This is not all obvious fact, but at least hopefully some of the intuition here is here. This happens to be integer, and it really captures how many times gamma winds around z equals to 0. And this is called the winding number. And you can obviously translate this, like you can change z to z minus a here, and then they'll capture how many times gamma winds around z equals to a. So I think it's good to keep in mind that these sort of things exist. Again, we're not going to deal with too many pathological paths in this video. We're just going to assume things are quite nice, but this is a true fact. So having talked about winding numbers, I do wanna go back and now talk about Cauchy integral theorem. Again, say we have some domain U here. And I'm basically going to consider gamma that looks like one counterclockwise rotation. So if I consider like say a point within here, then this looks like winding number 1, essentially. So with this gamma, and again here I'm going to assume the fundamental group of U is 0, so we have the simply connected domain. In this case, what Cauchy integral theorem says is that f of z, and by f of z I really mean any z inside this gamma, so this is z here. This is equal to 1 over 2 pi I times the integral of f of zeta over zeta minus z d zeta. Sorry, not dz, d zeta. So let's step back for a moment and think about what this says. What this is saying here is I want to evaluate this holomorphic function. So again, f is a holomorphic function. This is an underlying assumption in all of these theorems. So if I have a holomorphic function f from the domain to C, and I have some point z here, and I'm looking at the function value of z, it is really equal to integral around this gamma of like the slight change in the function, right? Rather than f of zeta, we have f of zeta divided by zeta minus z. But what we see here is that, like, imagine for a moment this z is fixed, right? So this z is fixed. And really now the variable within this integral that you're integrating with respect to is zeta. And this zeta is rotating around this path. So what I'm saying here is that the function value at this point inside a path is really determined by the function value around the gamma. And this again is extremely surprising. Like there's a connection between a function value on this path and the function value of any point inside. That's quite nice, and this is Cauchy integral theorem. And the proof is not hard at all, so I do wanna give a quick sketch. So the trick here is, since we know this is holomorphic, you know the difference quotient when I'm looking at it near z is bounded. And again, what I'm going to do here is I'm going to do a standard trick with the corridor. So rather than this gamma, you can just think about very small paths. You can think about very small paths, like let's call this gamma prime. And again, the integral along this gamma and integral along the gamma prime is going to be the same by considering a larger path, right? That looks that looks something like this, like the same argument we made before. So rather than thinking about gamma, we can just really think about gamma prime, where you're extremely close to z, and because of the holomorphicity, the difference quotient is bounded. So what I'm gonna do is I'm gonna look at this 1 over 2 pi I times integral of f of zeta minus c dz, and I'm going to write it as follows. So 1 over 2 pi I, and I'm going to introduce a difference quotient here. So zeta minus c d, sorry, okay, again here it should be d zeta, and again I'm integrating along gamma, and I want to add back integral of gamma of f of z over zeta minus c dz. So we have this equality. And here, because this difference quotient is bounded near z, because by this gamma I really mean gamma prime, because I'm really zooming in locally around z. And in fact, let's give all of these a name. So I guess we can keep this as original gamma if you like, and we can call these gamma prime. And here what's happening here is if I look at the absolute value of this integral, so if I consider the absolute value of this integral, where this dot is really the entire integral, this is bounded up to constant. So I'll use like this, like left sign to denote like up to a constant we have less than or equal to, up to a constant multiple. Well, what we have is the difference quotient, which is of course upper bounded by some constant, times the length of gamma, right? Times the length of gamma prime. So I'm just bounding an integral by the integrand, which is bounded above by constant, times the length of this. And by picking this gamma prime to be really small, right? By making this length go to 0, this entire part can be made to go to 0 by picking gamma prime, by letting length of gamma prime go to 0. And now let's look at this part. And this part, when I factor out f of z outside, so when I factor out f of z here, and I change this to just 1, then what we see is 1 over 2 pi I times integral of gamma prime of 1 over zeta minus c d zeta, once again, and this is just a winding number, right? This is just a winding number of gamma prime about z, and we know this is 1, just by assumption. So this entire thing is 1. So what we see here is that this entire thing is 0 plus f of z times 1. So this is just f of z. And that's the Cauchy integral formula. And the one reason this formulation is so nice, again I'm going to skip some of the detailed proofs here, is that just as the power series can be differentiated infinitely term by term, this integral, if you consider the right hand side of this thing can be differentiated infinitely many times inside the integral. So again, this requires some proof, and I think like Stein and Shakarchi and Ahlfors, at least Ahlfors for sure, I think, just does it in a bit of a brute force way where you actually literally write down the difference quotient, and then you actually show that it converges to what you want, which is like when you differentiate this with respect to z, then like for example, when you look at f prime of z, you would expect it to be 1 over 2 pi I times integral of gamma of f of zeta over zeta minus z squared d zeta, by differentiating with respect to z here, right? All of these are constant with respect to z. So this is just the usual differentiation. And you can show all of this is true, and you can differentiate this infinitely many times with the integral with the derivative that you expect. So in particular, when you differentiate it n times, then for example, when you differentiate this one more time, then you're going to get 2 factor out. Then when you differentiate one more time, the 3 factor is going to come out. So you expect n factorial over 2 pi I times integral of gamma of f of zeta over zeta minus c to the nth power, n plus 1 power d zeta. And this is in fact exactly what you get. And I'll ask you to look at, say, Ahlfors or Stein and Shakarchi for exact proof. And once we are okay with this, the fact that holomorphic implies analytic now follows pretty quickly. And the proof goes something like this, and I'm actually going to show something a little stronger than what you might expect. So like, again, if this is the domain U, and I have some point C here, or sorry, C naught here, what I'm going to consider is the largest disk around C naught that fits in U. So I'm going to actually show its analytic, not in just some like domain with positive radius r, but the maximal radius r that fits in the domain where you are holomorphic. So I'm going to consider, say, like a disk. like this. So this is R. So R is the maximal value like that you can go from C naught where you fit in this holomorphic region. And I'm going to show that we in fact have the Taylor series expansion that agree with the function value for every Z inside this disk. And how we proceed is as follows. So again, by Cauchy integral formula, we have f of z is equal to integral of 1 over 2 pi I times integral of f of zeta minus z d zeta. And let's say our gamma here looks something like this. I mean, maybe you are undefined like at the boundary here. So I can think about gamma that looks something like this. So you go around here, and this is gamma. So one's counterclockwise. And the key thing is you can make this gamma as large as you want. You can make it approach this capital R as much as you want. And the argument is going to go as follows. What we see here from this diagram, I'm only going to consider this C within the gamma. Again, you can make the gamma as large as you want, so you can really make this argument work for any C within this disk of radius R. But given all such C, the zeta that's rotating around, right? The zeta here is on this circular path. So what we see here is that when I look at the distance between C and C naught, and when I look at the distance between zeta and C naught, this thing is strictly less than 1. As long as I'm picking C within, say, like, I'll be a little informal here, within some disk like this, where this compact disk fits neatly within this gamma path. So for all Z uniformly, we have this condition. And this is going to give us some nice uniform convergence as follows. So I'm going to rewrite this as integral of f of zeta over 1 minus z minus c naught divided by zeta minus c naught, exactly inspired by this. And I think this is, again, an argument that I think I learned from Stein and Shakarchi in this case. And in this case, this is 1 over 2 pi I times integral of f of zeta times this infinite sum, integral from n equals to 0 to infinity. This is also a geometric series from like high school, c minus c naught over zeta minus c naught to the nth power d zeta. And the key thing is, because of this uniform condition, the convergence of the sum here is uniform. So by a standard real analytic theorem, we can switch the sum and the integral here. So what we get here is 1 over 2 pi I times the sum from n equals to 0 to infinity of this expression. So we have c minus c naught to the nth power. And we also have integral of along gamma of f of zeta over zeta minus c naught to the nth power d zeta. And where have we seen this before? Well, we have seen it exactly here, right? We also have 1 over 2 pi I here. So this is exactly f of c naught plus f prime of c naught, c minus c naught, plus f double prime of c naught over 2 factorial c minus c naught squared. And this is exactly the Taylor series. And this is exactly what we wanted to show, that our function f is in fact analytic. With Cauchy integral formula established, now I want to switch gears a bit and talk about like some of the difficulties in defining log of z. So when I say log, I really mean natural log as a holomorphic function. And of course, whenever you say a holomorphic function, like the question is on what domain. So what is the domain here? That's a critical question. And maybe like something that you intuitively think is, say, okay, log of 0 is undefined, but maybe I can at least define this to be like c minus 0. On c minus 0, maybe I can define log of z as holomorphic function. And it turns out this is not possible. In fact, you cannot even do this as a continuous function. And to get an intuition on why, let's first think about what log of a complex number has to be. Well, first of all, what is complex exponentiation? So when I start with a plus bi, so when I start with some complex number, and I raise e to the power of that, I get e to the a times e to the bi. And e to the a, this is a real number, and this is the modulus, right? This is the absolute value of the entire output. And b really determines the argument. This determines the angle of the final output. So when I want to take, say, like logarithm of, say, c plus di, so if I want to go backwards, then the real part that you're going to get out of it, it can be obtained by taking the usual natural log, so this is a real log, of absolute value of c plus di. So again, this is just the real log, plus I times the argument, the angle of c plus di, right? This is exactly analogous to the statement above. And the key thing is like this part is well defined and all. This is real log of a positive number. But the argument part, here there's ambiguity. Here there's ambiguity. Up to like integer multiples of 2 pi, because up to integer multiple 2 pi, because that angle is not well defined. I mean, if you're only off by like integer multiple 2 pi, you're actually the same angle. So when you try to define logarithm, you actually get a multi-valued function where there are many possible outputs up to addition of 2 pi I, right? Addition or subtraction of 2 pi I. So you might think, okay, why can't we not just pick something? Like, why can't we not just say, let's just constrain it? So let me first write this in a little bit of a nicer way. So maybe instead of c plus di, you can take logarithm of r e to the I data, right? If r e to the I data is c plus di, and all I'm saying here is this is log of r plus I times data. And one natural attempt you might try is you might just let this be like, say, 0 less than or equal to data less than 2 pi. Then you might be like really happy. You might be like, from this constraint, we're still capturing every complex number in the input. Okay, maybe other than 0, let's require capital R to be positive. But this captures all the numbers in C minus 0. And now everything is well-defined function. But the thing is, it is not continuous, right? It's not continuous because, I mean, if you think about in the input space, right? In the input space, so this is input space. Imagine you circle around in say like in a circle of radius 1, say, and you start at 1. Let's say you start at 1, and let's say you circle around in the input space. What happens in the output space? So this is going to C, and this is the output space. Well, from the way we defined it, so again, we're not going to count 2 pi. We're always only going to take angle that's at least 0 and strictly less than 2 pi. So at this point, we're saying angle is equal to 0. Where angle is equal to 0. So at the start point, when you take log of 1, you get 0 based on this constraint. And again, it's because of this constraint we get log of 1 equals to 0, right? If our constraint was 2 pi less than or equal to data, strictly less than 4 pi, then by this constraint, then log of 1, we would define this as 2 pi I, right? Because now this angle of 1 is now 2 pi. But we're using constraint here, so we are going to start at 0. And as you rotate around, this argument data is increasing towards 2 pi. So we're actually moving up in the output space up till 2 pi I, where you're not quite getting to 2 pi I, right? So there's a hole at 2 pi I. So as I'm circling here, I am moving up in this output space towards 2 pi I, and then we now clearly see you have a discontinuity problem by the time you circle back, right? If it's continuous, you wanna go back to 0, but you're ending up at 2 pi I when you circle around. So there is a continuity problem. And in fact, I think another way to think about this is if it was possible for log of z to be holomorphic on c minus 0, then I'm just thinking this, but then I think I'm fairly sure log of z, when you differentiate it, because of the fact that it's inverse of an exponential function, it needs to be 1 over z. So 1 over z would have an antiderivative. But if you have an antiderivative, then when you integrate a function with antiderivative along a closed path, right, along a loop, then you are guaranteed to get 0. If it's a closed path and you have an antiderivative, then by fundamental theorem of calculus, you can check this, you should get 0. But we know this is not 0, right? We know this is like 2 pi I. So we already know that log of z cannot be holomorphic on c minus 0. That's another perspective on this. But it is true that if we are willing to cut out even more things, so if we restrict u to be, so it doesn't contain 0, to be simply connected. So one example here would be constraining data to strictly between 0 and 2 pi. So in this case, actually maybe that's one way, but let's actually do something that where you keep the real line, so real log is still like consistent. So let's actually cut out from like minus pi to pi. So if you do something like this, then I'm only considering the part of the complex plane. So I'm cutting out this ray, right? This closed ray. I'm going to cut this out. And if you only care about defining log of z on this red region, this complement of this orange path, then it is true that you can define log of z in a holomorphic sense. In fact, how you can do it, let me just illustrate it. Let's actually illustrate it for the standard example. Like, so here, if this is 1 here, well, one thing you can do is you define log of z, if I want to define in the red region, to be integral from 1 to z of 1 over w dw. So when I say integral from 1 to z, I mean integral along any path. So if z is here, integral along any path from 1 to z. And the reason that this is well defined, like it doesn't depend on the choice of the path. Like I can also imagine, I can also take a path like this from 1 to z, and you don't want the integral to change. And that's because, let's actually think about this briefly. If you call the first path gamma, and you call the second path gamma prime, and I consider this purple path, which is traversing gamma, and then I'm going to traverse gamma prime backwards. Let's call it gamma tilde. Then integral of gamma tilde, because you are now in a simply connected region, right, of 1 over w dw is 0, because you're integrating on a simply connected region of a holomorphic function on that domain. This is a Cauchy. And clearly integral along gamma tilde is integral of gamma plus, because you're going the opposite direction, minus integral of gamma prime, and you know this is 0. So you know the integral along gamma and integral along gamma prime is the same. So this is again one of these like standard tricks. So you can actually define it to be this, and in particular we're defining log of 1. In particular we're defining log of 1 to be 0. And from this definition you can check that everything is holomorphic. So this is, I think, a Stein and Shakarchi way of doing this. But I think a bit of a nicer way, actually, if you know some basic covering space theory, is as follows. Like, what is really going on here is we have an exponential map from c going down to c minus 0. Exponential output is never 0, right? And what happens, say in this example, is you have c minus the ray from minus infinity to 0, which injects into c minus 0, and in particular this part is simply connected. And defining logarithm is essentially defining the inverse of this map. So you essentially want to define a lift. You want to define a lip, say like log of z here, such that this diagram commutes. When I apply this arrow and I apply this arrow, you get the same thing as applying this arrow, which is the identity map here. By identity, I really mean the injection. And because this is simply connected, as soon as I pick where one base point is going to lift to, so in this case, you can pick, say, like log of 1 to be 0 in this case, then there exists a unique lift. This is a standard covering space theory. And I guess here I'm implicitly assuming that you have an intuition on exponential function being really a covering map. This is a covering map. And I guess an intuition for this. Let's actually get a quick intuition. If I look at a base space of c minus 0, and I consider any point here, maybe this is angle theta and this is radius r, and I consider a small enough local neighborhood about this point. Let's think about what's happening upstairs. So if you look at what's happening upstairs, so this in this exponential mapping, so I'm thinking about what kind of points actually map to this local region around this point. Well, again, like we are going to have natural log of r. So log of r, the real logarithm of r as the real part. And we are going to have like data plus 2 pi, like data plus 4 pi, 2 pi I, 4 pi I, like these are going to be the y coordinates. I guess I can delete I here, like this is the imaginary coordinate. And what we're going to get is roughly something like this, right? We're going to have little neighborhoods here, and each one of these are going to project down to this local neighborhood. So we have a local homeomorphism, right? We have a local homeomorphism. So this is a covering map. So we do have this unique lift. And locally, since exponential function is an extremely nice function, right? It's certainly holomorphic. So you actually have a local biholomorphism here. By biholomorphism, I mean the function is holomorphic, and the inverse, with all the appropriate restrictions of domain and codomain, the inverse is also holomorphic. So holomorphic two ways. Since you have a local biholomorphism here, locally log of z can be obtained by going this way and then going backwards following this local biholomorphism. So since this is holomorphic and this is holomorphic, log of z is holomorphic. So that's yet another way to think about it, which I think is even nicer. Continuing on, now I want to cover some of the really beautiful theorems in complex analysis, like open mapping theorem, maximum modulus, and Liouville's theorem. And the way I'm going to present it is I'm going to follow, I believe, it's been some time since I read it, but I think the approach of Forster's Riemann surface book. I think Miranda's Riemann surface might also have some nice proofs that I referenced some time ago. And the way we're going to go about it is by developing a basic theory of just the Riemann sphere, the CP1. So CP1 is really just a sphere. This is CP1. And how you should think about it is it's really a complex plane along with the point at infinity. So topologically, this is a one-point compactification here. And the usual way of thinking about this is if I have like complex plane and I have this sphere on top, and infinity is really the North Pole. This is the topmost point. And you really have the correspondence between the CP1 and this complex plane other than outside of infinity by just shooting the point outward. So if I have like this point here, I'm going to correspond to it. So if I think about a ray that goes through and then like it disappears and it goes through this plane, I'm going to correspond this point with this point. So for example, an open set even topologically speaking, if I have an open set here in CP1, then I'm corresponding that with an open subset of C like this. Whereas like if you know the theory of one-point compactification from like say the point set topological part of 55, then the neighborhood around infinity would look something like this, right? So you should think of it as you have the complex plane, C, and you have any compact set. So maybe this is K, this is compact. And if you think about everything outside of this compact set, so everything here, along with infinity, this would be a neighborhood of infinity. And I guess on the sphere it looks something like this, right? It's just a neighborhood around infinity on the top. And we want to give some complex structure to this so we can talk about what does it mean for something to be differentiable function from like CP1 to CP1, for example. So, I mean, let's say now we have a function f from like CP1 to CP1. And let's think about what does it mean for this thing to be holomorphic at infinity. And I think the most elementary way of thinking about this is you have, again, CP1 here, and I'm mapping to CP1. But let's say like just for the sake of simplicity for now that you're mapping to some point that's not infinity. So here you have infinity here, and our f is mapping it to f at infinity here. And let's just assume this is not equal to infinity. So we have some point here in the complex plane. And how you can think about the differentiability of this function is you can correspond this neighborhood at infinity with a neighborhood of 0. So if you consider this to be a complex plane C, and 0 is right here, and you can think about some neighborhood near 0, and you can think about some local homeomorphism between these two open sets by just the map 1 over Z. So here 1 over Z, in particular, I'm assuming it maps the 0 to infinity, and this 1 over Z gives you a local homeomorphism here. And what you can do is by considering this composition, which is local, but local is all you need for differentiability. So when I consider this composition, you just check whether this is holomorphic at 0. And if this thing is holomorphic at 0, then you just say this function f is holomorphic at infinity. Again, it's because I'm just identifying this open set with this open set near 0. And I'm really identifying this function f locally with this function, right? From really a C2 or open subset near 0 to complex plane. So this is how you think about holomorphicity at infinity. This is like one of the simplest case of like a Riemann surface sort of identification. And you can also do the same thing. Like if I have like a map again from like CP1 to CP1, and now let's say like I have some point, say Z, that's mapping to infinity. And if I'm mapping to infinity, what does this mean to be holomorphic at Z? Holomorphic at, let's just give it C naught to emphasize just a single point. What does it mean for it to be holomorphic at C naught? Well, again, you do some sort of local identification. Like, again, I mean, it can be infinity. If it's infinity equals to C naught, then you do a local identification here. But if it's not, let's say this is C naught, and then I'm mapping by F, and this C naught is getting mapped to infinity. And what you can do is now, rather than doing the identification here in the domain space, I can do it in the codomain as well, right? I can just think about this 1 over Z mapping, which is going to map this set to some local neighborhood around 0. And once you do this identification, what does it mean for this thing to be holomorphic at Z naught? Well, you just consider this map, which is now going to a complex plane that you're just so familiar with, and you just check whether this is holomorphic, right? So using this, like, and this is also definition, right? I'm defining this to be holomorphic. I'm defining this arrow to be holomorphic when this arrow is holomorphic, and I'm defining this arrow to be holomorphic when this arrow is holomorphic. And really the only trick is, since we don't really have a concept of like differentiability when the output is infinity or input at infinity, you just do this trick of identifying the area near infinity to area near zero in the complex plane where everything is nice. And the main fundamental theorem that's going to drive everything from here on is that if I have a map F from CP1 to CP1, and let's say this is holomorphic, right? Like, one thing to realize is locally, so if I just pick any A, so pick any A, locally near, when I zoom in locally, so so A in the domain, right? And F of A in the codomain, you can first make this identification. Sorry, I haven't really gotten to the proof yet, but let's first sketch out what I'm trying to say. So again, you have some A here. It can be infinity. I mean, the argument is really the same. The argument is really the same up to this 1 over Z sort of composition. And let's say F of A, your F of A lies somewhere here. Well, what you can do is you can make a local identification of neighborhood near 0. So let's say this is 0 with a neighborhood here. I mean, if A is infinity, then you use 1 over Z. If A is not infinity, then you just subtract A. Like in this case, like if A was actually on the complex plane, I'm just moving this open set to the origin. So that's one possibility. We're not exactly going to do this, but my point is this is possible to identify A with 0. And again, using something similar, you can identify a neighborhood of F of A to just a neighborhood of 0 in the complex plane. So the point is, you can certainly up to this like local homeomorphism here, the map F can really be thought of as this map F. If again, like these two are not really the same map, but by applying F and applying this, you really get a map that sends 0 to 0, which really should have the same properties as little f, locally speaking, right? With respect to this small region. And the theorem and the fundamental theorem is you can in fact do this because here like we pick the translation, like in this specific example, but you don't have to pick translation. You can pick any sort of local homeomorphism identification here. The theorem is I can actually pick this and I can actually pick this such that we can make f locally not only send 0 to 0, but it's of the form Z mapping to Z to the n for some m greater than or equal to 1. So it's just Z raised to some power. So I'm saying like by picking the right map here and correct map here, this map is just going to be Z mapping to Z to the n. Assuming, so I guess the only counterexample really here is assuming f is non-constant. If f is a constant map, then certainly you cannot have it locally equal to like Z to the n's power. And to see the proof, you proceed as follows. First, let's assume we got this 0 to 0 done. You either use 1 over Z here or you use the translation. So we did get it to 0 to 0. And we are just trying to, so we can make this commutative diagram a little more fancy, right? So once we got this map, sorry, this is getting a little dirty here. Once we got this map to send 0 to 0, what you can do is you can come up with some local biholomorphism here. If I can come up with some biholomorphism here, and if I can come up with some biholomorphism here, and this is a more general case, and then this map, now that's going from here to here, sends it 0 to 0 and maps Z to the n's power, then we are done, right? So I'm just saying like this part can easily be achieved, and I'll just compose with one more biholomorphism to form the third map. So how do we get something like this? Well, first of all, because f is non-constant, and now I'm going to focus on this 0 mapping to 0 case, if I look at it locally and I look at the power series expansion, it's going to look something like this. You're going to have the first coefficient that's non-zero, so say an, without loss of generality, this is non-zero, and you're going to have like, say like an plus 1 z plus an plus 2 z squared, and continuing on. And here n is greater than or equal to 1. And now the thing to realize, let me erase the top part, is that if you call this entire part, g of z, then we can write g of z as h of z to the nth power for some h where like restricted to the local region that we are working with. This is holomorphic, and I mean this is just a matter of realizing that h of z can be defined as e to the 1 over n times log of g of z. I mean this is you should just think of this as g of z raised to 1 over n's power essentially. And if you're worried about how to define this log of g of z, I mean, you can again use some sort of integral definition, or if you're comfortable with covering spaces, then you essentially again have a map from c to c minus 0 given by the exponential. And now in this simply connected neighborhood, I'll assume this is simply connected, you have a map from u to c minus 0 given by g of z, and then you can get this lift, which is exactly log of g of z. So you can define all this, and what this means is we have z to the nth power times h of z to the nth power here, h of z to the nth power. So this entire thing is really z times h of z to the nth power. So to finish, we can just show that this map. So to finish, we can just show this map from z to z times h of z is a local biholomorphism. So we can show this. Then this is exactly the coordinate change, right? This coordinate change we needed in the domain to really just get it as your coordinate. So if you think of this as new z, or you can think of this as being w if you like, in the new coordinate, it's just w to the nth power. And this is exactly what we wanted in the theorem. So we just have to show that this is a local biholomorphism, and how we can do it is use inverse function theorem. Inverse function theorem says that as long as the derivative is non-zero, so this is a complex version of like inverse function theorem, as long as the derivative at the point is non-zero, then we in fact have a local biholomorphism. So let's just differentiate. So let's just differentiate z times h of z, and this is exactly h of z plus z times h prime of z. And when you evaluate this at z equals to 0, which is the point in question, this thing becomes 0, and we know h of 0 is non-zero, precisely because g of z here, g of 0 is not equal to 0, so h of 0 cannot be 0. So by inverse function theorem, we in fact have this. So in summary, if you have a map from CP1 to CP1, then locally it just looks like a map from z mapping to z to the nth power. So again, this is holomorphic here, and this fundamental fact can now be used to derive so many things. Like for example, let's first derive what's called the open mapping theorem, which says that if I have a holomorphic map from C to C, so this is holomorphic and non-constant, then F is an open map. It carries open sets. The image of open set is an open set. And what's the proof? Well, locally it just looks like Z mapping to Z to the nth power. So again, I guess I forgot non-constant here. So locally it just maps. It looks like Z mapping to Z to the nth power, and that is clearly open. Because like what does R e to the I data, when I raise to nth power some complex number, what does it do? I just exponentiate the modulus, and I just rotate around the angle. I just change the angle to n times what it was before. So really, like if this is the input space, and this is the output space, and I consider like some neighborhood like this, then all that's happening is I'm in the output space. Okay, I'm not super sure where it's gonna go. Like maybe you're squaring it, so now you're like here, and maybe you get something like this, just further away. But it is clearly an open map, and from the open mapping theorem, we also get the maximum modulus. I forget if it's maximum modulus theorem, maximum modulus property, but I can tell you the statement. If I have like some open set U in C, and I'm going to assume this is pre-compact. So by pre-compact, I just mean when I take the closure, you get a compact set. So if I have a set like this, and I consider F from U to C, or also just to make one correction, I guess like in the open mapping theorem, it didn't need to be C. It could have been any open domain here. And no pre-compactness required here, but I do require pre-compactness for maximum modulus. So if I have F from U to C, so your F here is mapping to the complex plane, right? So F here is going all the way to complex plane. And let's make sure that F is defined in the boundary too. So I'm going to assume here that F is holomorphic in U, and F is like continuous in U bar, right? In this compact set. So in particular, since F is a continuous map on a compact set, you know F achieves a maximum. This is just a standard real analytic fact, nothing special so far. So we know F achieves a maximum. But where can the maximum be? Well, maximum modulus theorem says you cannot have maximum in the interior. You cannot have a maximum that's not on the boundary of U. So like there cannot be a point here like C0 where we get a maximum. If we for the maximum of f, the maximum value can only be attained on the boundary. So this is what the theorem says. So then maximum of absolute value of f, to be precise, occurs at the boundary. And the proof is rather fast from open mapping theorem. Like say I have a point here. Just pick any point that's not in the boundary. So you have some open set around it. So let's call this C0, and you're going to map to some f of C0. I claim. So only thing we have to show is it suffices to show there exists some C1 such that absolute value of f of C1 is greater than absolute value of f of C0, right? So I just picked an arbitrary point that's not in the boundary, and now I'm going to show there exists some C1 where the absolute value of f at that point is actually larger than f of C0. So that will finish the proof. And how do we do that? Well, we know f is an open map, so we know when we carry this through, you got some open set here. Like the image of this ball is actually an open set here. And since it is an open set, I mean, like the point like this, we know this point is further away from 0 than f at C0. And we know because like this is the image of this ball, we know there must have been some point, say like C1, somewhere in this ball, that actually mapped to this point, f of C1. And since f of C1 is further away from 0 than f of C0, that's exactly what we want. So that's the end of proof. And another consequence, actually, before we get to another consequence, let me actually do a quick interlude to give one application of maximum modulus principle, which on its own also has tons of applications, and that's called the Schwarz lemma. And Schwarz lemma says the following: if I have a holomorphic map from the open disk, so this is all absolute value of C less than 1, so this is an open disk, open unit disk, to complex plane, so this is holomorphic, and I'm going to assume 0 gets sent to 0, and I'm also going to assume that absolute value of f of z is always less than or equal to 1. So given these assumptions, there are a few things to conclude, but let's actually just think about it. And what can be concluded. So given the setup, so this is the setup. Consider the map. C maps to f of z over z. One thing to realize is that this is also well defined. This is also well defined and holomorphic, and it can be made holomorphic, to be precise, at c equals to 0, because this f is differentiable at 0, and when you take the limit as c goes to 0 of f of z over z, this is exactly a difference quotient, right? Because f of 0 is 0, so this is f prime at 0. So this is well defined and holomorphic at c equals to 0, with 0 mapping to f prime of 0, if you like. And let me assume something a little stronger just for the moment. Let's just assume that f is also well defined at c less than or equal to 1. Just for the moment, let's say f is well defined even at the boundary of the unit disk. Assuming that on the boundary of the disk with absolute value of c equals to 1, what happens? Well, this f of z over z function, well, absolute value of z is 1, so this part becomes 1 when you take the absolute value. And f of z is at most 1. So by the maximum modulus principle, you must have f of z less than or equal to absolute value of z for all z within the disk as well. Because this less than or equal to 1 was holding at the boundary, and if the maximum of this function occurs, it needs to occur at the boundary. So within the interior of the disk, this less than or equal to 1 still has to hold. So we know this is actually true for every z. So this is one nice application. Now, if you don't like the fact that I all of a sudden assumed f is well defined on the boundary of the unit disk, which honestly may not be true, then I think the argument I've seen process like something like this. If this is the unit disk D, so here the radius is equal to 1. Since we cannot assume the function is defined in the boundary of D, just consider any radius r that's smaller than 1, and do this sort of idea, but at absolute value of z equals to r. Do this and let r approach 1 from the left, and then this will get you exactly the same conclusion in the end. So we know this is true, and again, I'm sorry, I'm dropping some hypothesis here, of course. Like when I was saying maximum modulus principle, we were using the open mapping theorem. So a fundamental thing here is that this is non-constant, right? If it's constant, then maximum occurs everywhere. So I guess something to be pointed out here is if we have equality somewhere. So I guess this is part of Short's lemma. So this is one conclusion from Short's lemma. But another conclusion from Short's lemma is if absolute value of f of z is equal to absolute value of z for some c and d, then this must mean the maximum was attained here. The maximum was attained in the interior. So we must have f of z over z is constant. And since absolute value of f and absolute value of z was the same at some point, well, we must have f of z is equal to z times some number, let's call it a, where this a has absolute value 1. And what does it mean to multiply by a complex number with absolute value 1? Well, this just means it is rotation by some angle. So this is rotation by some angle. So this is another conclusion you can derive. That's part of the Short's lemma, that if you do have equality within the disk, then you are actually just rotating by some angle. And now thirdly, the thing I want to mention is Liouville's theorem, which states that if I have a function f from c to c that's bounded, so the output is bounded in some compact set, and it's also entire. Entire just means it's holomorphic, with like the domain being the entire complex plane, which is the case here. So if you have a bounded entire function, then it turns out f is just constant. Then f is just constant. So you actually cannot have a differentiable map that's defined everywhere in the complex plane that is bounded if you're not constant. That's again quite crazy, right? Like you can just think about like x mapping to cosine of x. This is bounded, this is differentiable everywhere on R, but it is actually not a constant map. So obviously this is not true for functions of real numbers, but it turns out for the functions of complex numbers, bounded and entire means it's constant. In fact, if you define cosine of z, the usual way, like for the complex numbers, you can define this as what? E to the iz minus e to the minus iz over 2 using the Euler's formula, right? I mean, you can see that this is actually unbounded. Because I guess you can just let z be like r times I. Then I guess as r goes to infinity, then absolute value of cosine of z should blow up. Because when you plug in ri into here, that's e to the minus r. That goes to 0, but here you have e to the plus r, and that blows up. So cosine is actually an unbounded function when the input is complex. So that's not a counterexample in the complex case, in fact. And Liouville's theorem is true. So how do we show this? Well, the first thing to realize is you can actually extend it at infinity. So I claim, so this is a claim, is I can actually extend this function as a map from CP1 to C. That is still holomorphic here. So the key question is, how do I know that you can give a well-defined definition at infinity and you are actually holomorphic around it? So and that really is a question of checking if I, again, have this map F, and I consider the map from like say C minus 0 to C given by just 1 over Z. I really want to check that this map has a removable singularity. So you want to show this as removable singularity at Z equals to 0. By removable singularity, I mean you can define the value of this map at Z equals to 0 in a way that this composition is actually holomorphic, right? You can fill in a value at Z equals to 0, and then everything is holomorphic. This is really the same as trying to fill in the value of the input at infinity here and making this map holomorphic. And the reason this is true, is clearly like to realize that this function is bounded near Z equals to 0. A priori, it's not defined at Z equals to 0, but because this function is bounded, we know this function is also bounded, as long as you're not exactly at 0. And I claim that this is a well-known theorem of Riemann. This implies that we actually have a removable singularity. So this is another key theorem, that boundedness in a punctured disk, right, near that point, actually implies removable singularity. And I think the way that Ahlfors, approaches this is something like this. I'm not sure if the book argues with the same details, but I think the intuition, is that like if I consider this disk near Z equals to 0, and I consider any point C here, and let's give this path name gamma. And something I can do is I can again do some sort of corridor trick where I consider a path like gamma prime here, which is more local around Z. And I can also consider like a larger path that goes like, the trick I we've seen many times, that goes something like this. And because of that, when I consider integral of gamma of f of z over zeta minus c d zeta, then this is equal to integral of gamma prime of f of z over zeta minus c d zeta. And by Cauchy's theorem, because like obviously there's no problem, no singularity here. There might be singularity here as far as we know, but there's no singularity, nothing blowing up around here. By Cauchy's integral theorem, this is equal to f of z. So we actually have for every point outside of 0, so for all z not equal to 0 within this disk, we have the equality that this integral is equal to f of z. And now the key thing is that this thing just as a function on its own, just forget about this equality with f of z for now. If you just look at this integral, I hope I'm not lying to you right now, it is infinitely differentiable. This is infinitely differentiable with the integral that you expect differentiating under the integral. And that includes at z equals to 0. So for this thing, we're not relying on the fact that f is not defined at 0 at all, right? Because you're only integrating for values along this path, which here, none of the values zeta is equal to 0. So this is a well-defined forever differentiable function even at z equals to 0. So we actually get f of z is equal to, even at z equals to 0, something that's holomorphic at z equals to 0. So this will show it, but again, where did I use boundedness near z equals to 0? This was kind of swept under the rug, and I really should mention that. And that really is mentioned when I did this trick of using gamma and gamma prime equivalence. So let's be actually more precise. So the path I really looked at is a path that looks something like this. I guess if we trace out the longer path, this is a bit of a technical thing. I guess here we want to move in this direction, we want to move in this direction in the opposite way on the same segment. But I think usually you might assume the fact that it doesn't really have self-intersection in maybe some of the proofs. Again, I'm not super sure, but if you want to be precise, you can do something like this. You can imagine this as being the gamma tilde, where this was 0 here. And a fundamental thing that you needed to show equivalence of integral of gamma and integral of gamma prime is that integral along gamma tilde is equal to 0. Like for this f of z over zeta minus c d zeta, right? If this thing is not 0, then obviously all the argument here fails. So how do you show this is 0? First of all, you might be concerned by the fact that I'm not exactly using like these two corridors overlapping each other perfectly. But this is not a huge concern because you can just take the limit. You can just take the limit of these gamma tildes where I move these two parts closer and closer, and in the limit it is going to go to exactly the thing you want, where you do have a cancellation at the corridor. And the fact that you can do this without any issue is, again, I'm skipping some details here, is that you in fact have uniform continuity. If I consider a compact rectangle here, you have a uniform continuity of this integrand within there. So we don't have to worry about some weird interchange of limits, breaking or anything like that. And to show this, well, what you do is you actually create another corridor near 0. Again, the fact that you do not have this immediately from Cauchy's theorem is because Cauchy's theorem requires you to be holomorphic in the entire interior. But currently, we don't know what's happening near z equals to 0. So I'm going to create another corridor, and then this essentially breaks it up into a loop like this. So let's call this larger path gamma red, and essentially the gamma tilde part now is being broken up to gamma red part and say gamma this tiny circular part. So just the part that's rotating around 0 here. So let's call this gamma local. So it's local near z equals to 0. So we essentially have this break because the only problematic point of the integrand is really, and again, I guess here I do have a typo, so apologies for this. So I really meant f of zeta here, just based on the Cauchy integral theorem. And the only part where this integrand, which is a function of zeta, has a singularity potentially, is when zeta is equal to z, which we got rid of because z was here, or when f has a problem, which is at 0, which we also removed by isolating that to this gamma local. So you know this part is 0. And really, you just have to argue this integral of gamma local part also can be made as small as possible by making this disk as small as we want. And the argument can proceed as follows. So again, let me write some of this down. So essentially here, what we want to show is that by making this gamma local small enough, this part can be made to go to 0 for gamma local, for the length of gamma local essentially going to 0. So again, gamma local is this circular path of, say, like radius epsilon around 0. And one way to think about this is that if you let this be g of zeta, then we see that limit as zeta goes to 0 of zeta times g of zeta, let's take the absolute value here as well, is equal to 0. And the reason for this is exactly the fact that we have this boundedness condition near z equals to 0 for f. So when I multiply by zeta here by doing zeta times g of zeta, then the numerator is going to go to 0 and the denominator is staying away from 0. So we do in fact have this. And if you try to bound this integral, if we want to bound this integral gamma local g of zeta d zeta, then up to, I'll use this less than sign again to denote less than or equal to, except I'm suppressing like say some constant multiples. Then this should be less than the length of gamma local times the maximum of say zeta, maximum of zeta in this gamma local of absolute value of g of zeta, right? And here the length of gamma local, because gamma local is again just a disk centered at 0, this is really up to less than, up to a constant multiple, really just the absolute value of zeta, where zeta rotates around the gamma local. So this really is less than maximum of zeta in gamma local of zeta times the g of zeta absolute value, and this we know goes to 0. So we know this goes to 0 as well. So by making this gamma tilde as small as we want and running all of the arguments that we previously made, I think the proof should go through. It's possible that I missed some subtle point here, and if so, please like correct me in the comments. Like feel free to do that for anything in this video really. But once we have this established, we know up to this filling in removable singularity, f can be viewed as a holomorphic function from CP1 to C. And now let's think about what kind of we can derive from this. So first, let's assume it's not constant and try to get a contradiction, right? So if it's not constant, open mapping theorem kicks in, right? Open mapping theorem kicks in to say like f is open. So when I look at the image of f of CP1, this must be open. Again, this is the open mapping using non-constant. And because CP1 is compact and f is continuous, we know f of CP1 needs to be compact. And because CP1 is connected, we know f of CP1 also needs to be connected. But now think about what needs to be true. We have an open, closed, connected subset of C, and C itself is connected. So this must be the entire C, right? This is certainly non-empty as well. But C is not compact, so you already get a contradiction here. So this is a Möbius theorem, and in fact, there's actually a vast generalization of this. I think if you're interested, you can look up things like Picard's theorem. Second fundamental theorem, Neval-Lina theory, also is a vast generalization. But we will not talk about any of those, and having established these basic results, now let's move on to another nice thing in complex analysis, which is like, I think from what I heard one of the professors say, it's really a party trick, which is for evaluating some integrals. And in order to do so, I want to introduce what's called a residue theorem, which is pretty fundamental in its own right. And to do so, I want to introduce the notion of a pole. So far, we have seen the removable singularity. And there's another thing called essential singularity before we get to pole. Essential singularity. And I think a classic textbook example, I think from Stein and Shakarchi for this one, is e to the 1 over z. And consider what's happening at z equals to 0. If I approach, so in the complex plane, if I approach along the negative real axis, so here z equals to 0, and I consider plugging in things like negative 0.1, negative 0.01, negative 0.001 into e to the 1 over z, then e to the 1 over z here is going to approach, like this is going to be e to the minus 10, e to the minus 100, e to the minus 1000, that's going to go to 0, right? On the other hand, when I approach On the other hand, when I approach from the positive real axis, 0.1, 0.01, 0.001, then e to the 1 over t, this blows up, right? This blows up to infinity in magnitude. And if let's do one more. If I approach from the positive y-axis, this is like 0.1i, 0.01i, 0.001i, then I get something like e to the 10i, e to the 100i, e to the 1000i, right, as the output. And all of these have magnitude 1. This is just angle being radian 10, angle being radian 100, angle being radian 1000. So you're just circling very rapidly on a unit circle. So this is like output is circling unit circle. So something like this is called essential singularity, where you're not just blowing up towards infinity uniformly as you approach t equals to 0, but the very chaotic behavior really occurs depending on how exactly you approach the singularity. So that's one example to keep in mind, and there are many interesting results on essential singularity. Certainly Picard's theorem, I think, is one of them as well. But perhaps the tamest sort of singularity, other than removable one, of course, is a pole. And how you should think about it is, this is a singularity, so you're not holomorphic at one point, but this is a singularity where when you approach a pole, you blow up towards infinity, no matter how you approach it. So this is like you blow up in magnitude as you approach pole. To make this a bit more rigorous, so let's say you have a function f, and let's say f of z has pole at z naught. What this means essentially is, if you look at 1 over f of z, then how you should think about it is, when you plug in z naught, this thing is essentially infinity uniformly in all direction. So you should think of 1 over f of z as having a 0. So this has a 0 at z equals to z naught, up to removable singularity here. So for example, a trivial example is, say f of z is equal to 1 over z squared at z equals to 0. This is a pole. This is a double pole of order 2. When I look at 1 over f of z, then up to removable singularity, this is really z squared, and this has a 0 at 0, right? So this would be one example. But if you look at the power series expansion, of this, you're going to get z minus z naught to n's power times some g of z. So what I'm doing is, I'm looking at the power series expansion. I'm going to take out the smallest power of n that I can take out from the power series expansion. Again, the constant term is 0 because we have a 0 at z equals to z naught. And here we know g of z naught is not equal to 0. I mean, if this is not clear to you, I mean, just write down what's a power series at z equals to z naught. This is like a naught plus a1 z minus z naught plus a2 z minus z naught squared, and so on. And here we know we have a 0 at z equals to z naught, so a naught is 0. So you just look at these coefficients, take the smallest one that's non-zero, and then just take out z minus z naught to the nth power, and you're going to get something where when you plug in z naught, this should be non-zero, right? So you can get this. So in the case of a pole, what this is telling you is you really have what's called a Laurent series, where rather than a power series, we actually have negative exponents. And to see this, you just invert once again. So this is f of z is equal to z minus z naught to negative nth power times h of z. And because g of z naught is non-zero, h of z is a reciprocal of g of z, and this is well defined because of this, even at z naught. So this is a locally holomorphic map near z equals to z naught. So here this equality is really only true locally. And doing now a power series expansion of h of z, we are going to have this is equal to z minus z naught to minus nth power times a naught plus a1 z minus z naught, a2 z minus z naught squared, and continuing on. And this gets you a naught times z minus z naught to minus nth power, a1 z minus z naught to minus n plus 1 power, and so on. So we get this power series expansion where we start with some negative power, and then now you start going up, rather than starting at the zeroth power. And this is really what happens near a pole. So again, this is called the Laurent series. And given this, now let's actually think about what an integral of f is going to be. So if I have, again, f from u to c, and let's say this is meromorphic. So meromorphic This is a new term I'm introducing here. This just means holomorphic other than the pole, other than having some poles. Holomorphic, but outside of some poles. And to be concrete, let's consider an example where, okay, so maybe this is U, and we are integrating. So let's have some path gamma here, and let's say we have two poles. We have a pole here, and we have a pole here at say C0 and C1. Now let's think about what is an integral of along gamma of f of z dz. Well, again, we can do the sort of usual trick where you have a corridor, you have another corridor here, and you integrate here and you integrate here. So let's calling the smaller circle here gamma 1 and calling this like smaller circle gamma 2. You can show that this is really integral of gamma 1 of f of z dz and integral on gamma 2 of f of z dz. So using this trick, you can essentially divide up this integral into like two local integral where I'm just circling around, each of the poles separately. So let's focus, let's zoom in on gamma 1. So again, here we have C0, and then I have like gamma 1, which is circling it, gamma 1 like this. And because Z0 is a pole, we're going to have a Laurent series expansion that looks something like this. We have f of z is equal to, say, like c minus c0 to minus n, or say like a at minus n plus c minus c0 minus n plus 1, a minus n plus 1, and I continue on to c minus c0 to minus 1 power, a minus 1, and then you have a0 plus a1, c minus c0, and this continues on. So you have this Laurent series expansion near c0 here. And the thing is, what happens when I try integrating? Well, the thing to realize is all of these powers, c minus c0 to minus, like, say, 10th power, c minus c0 to minus negative 9th power, and say c minus c0 to negative 2nd power, all of these have antiderivatives. So all of these have primitive. So by primitive, I just mean complex antiderivative. And if you have an antiderivative, by fundamental theorem of calculus, when I circle around, then you're going to get a 0 for the integral. And that's also true for a0, c minus c0. All of these have primitive. And the only term really that we've seen before that doesn't really have primitive is this term, because natural log of c minus c0 is not well defined, right? When in this puncture disk away from c0, you actually have to take out a ray or something for it to be fully well defined. So what we actually get here is that integral of, say, this gamma 1 of f of z dz is really just integral on gamma 1 of this a minus 1 over c minus c0 dz, and we've done this calculation before. We did a center that c0 equals to 0, but it's really the same calculation. It's just integral of 1 over c dz around the circle, around the center point, and this was 2 pi I. This was 2 pi I. And because the output integral turns out to be so simple, it's really just the 2 pi I times this magical number, this coefficient of the negative first term in the Laurent series. This actually has a special name, and this is called the residue. This is called the residue of our function f of z at z equals to c0. I mean, I'm not sure what's the correct notation, but this can be one of them. The conclusion from all of this is, since you can do the same thing for gamma 2 as well, is that integral of gamma of f of z dz is really 2 pi I times the sum over all the residues, where I'm summing over every pole. So this is a famous theorem, and this actually allows you to calculate some integrals called the residue theorem. I think it's good to see one application of this, so let's dive in right away. So here I copied the residue theorem just one more time, the integral of our function. Again, I guess I should say gamma really has winding number 1. Just, for example, just a one counterclockwise circular arc divided by 2 pi I is really the sum of the residues of the function. So the key integral I want to evaluate for this one, let's give one example. This is, I think, standard textbook one, is integral from 0 to infinity of square root of x divided by x squared plus 1 dx. And this will not only give application to residue theorem, but also allow us to talk about like picking branch cuts for square root of x function. And to dive in, this is what is going on. The first thing to realize is this is also a real integral, right? There is no complex analysis as far as you can tell by just looking at it. And the way to do this using complex analysis, again, this is sort of a party trick, is to proceed as follows. So if you consider the complex plane, so this This in particular is the real axis. The integral that we initially wanted to evaluate is this one. We wanted to start at 0, and you wanted to go towards infinity along the real line. So this is the path that you're integrating. So that's what we want to do, but we're going to do something slightly different. What we're going to do instead is we first consider the function square root of z divided by z squared plus 1. There's some subtlety here, I'll get to that soon. When we're going to integrate it along a path that looks something like this. So I'm first going to move along, I'm not quite going to go along the real line, but maybe like epsilon distance above the real line. And then I'm going to circle around. Maybe this big circle has radius capital R. And then I'm going to come back down the same sort of corridor. And here I'm also going to circle. And here maybe circle with radius epsilon. So again, my entire path looks something like this. I go like this, I go around the circle of radius R, I come back, and then I circle the radius epsilon. So let me call this entire path, so this entire contour, let's call this entire path gamma contour. So gamma contour is the entire path that you see here. Obviously it depends on R and epsilon, that's implicit. And we also have the two horizontal paths, and let's give this path a name. Let's call this gamma right. And we also have this path which is gamma left. Let's call it gamma left. And we also have here gamma epsilon, and we also have gamma r, where gamma r is really rotating counterclockwise around the circle, and gamma epsilon is really rotating, I guess in this case, clockwise, right? The way I'm moving around the circle of radius epsilon. You might be like, I mean, there's technically this gap here, so it's not a full circle of radius epsilon. All of these claims can honestly be justified rigorously. I mean, essentially, the key thing you need is you have some uniform continuity of this function, like say in this compact rectangle. So you can make this distance. Between gamma right and the real axis and gamma left and the real axis as small as you want. You can compress it as far as you want. And in doing so, you can make this gamma r approach the full revolution, and gamma epsilon also approach like a full revolution. So there's some hand waving here, but all of this can be justified. Before we talk about why am I integrating along this gamma contour, let's talk about some subtlety inherent in this f of z equals to square root of z over z squared plus 1. And the main issue here is just like natural log is multi-valued, square root of z is also multi-valued, and you cannot just make it holomorphic everywhere like you like it to. So square root of z, when you look at square root of r e to the I data, this is really square root of r times e to the I data over 2. And the thing to realize is, like, I mean, take for example, consider data equals to 0 and 2 pi. Like, these two are different angle, but the input r e to the I data is still the same, no matter, even if you choose 0 or 2 pi. But the output of square root of x, actually it depends, right? When data is equal to pi, this is I pi, and that's minus 1. So that actually gives you a fundamentally different output. This is like kind of giving like square root of like 4, and you're getting like plus or minus 2, for example. So we do have this sort of concern, and this sort of multi-valuedness. You can make the same sort of intuitive argument by circling around the input space, and the angle is always 1/2 of that if you try to pick it in a consistent way. It really means you cannot make the square root of z. You cannot make the square root of z, even a continuous function in all of complex plane. So if you want to make this a holomorphic function, you again have to take some branch cut. By branch cut, I mean you have to remove, like say a ray to make sure like the resulting points, the resulting space is simply connected. So in this case, what I'm doing here, I mean, this is not the only reason I'm doing it, but this is one of the reasons we're forced to. I'm taking out the real axis here. The positive real axis is being taken out. So essentially, what I'm doing here is to make these sort of problems obsolete. What I'm doing here is I'm only considering data between 0 and 2 pi strictly. So I'm not going to consider any point lying on this positive real axis. And in doing so, this makes square root of z holomorphic, where we are actually trying to integrate here. And now you're probably curious on how is this helping evaluate our integral? Well, notice this. So let's consider the limiting case where gamma right and gamma left really moved basically just on top of the real line. So gamma right is just moving along the real line from 0 to r, and gamma left is moving on the real line from r to 0 in the leftward fashion. In this case, let's think about what is integral in the limiting case, right? What is integral of gamma right of square root of z over z squared plus 1 dz? Well, if you're literally on the real line, and I mean, you can make it however you want, but let's say you're going from epsilon to r if you like. So here you're moving from epsilon to r on the real line. In this case, okay, I guess I'm being a little hand wavy here because of course square root of z is not well defined on the positive real axis the way I'm choosing the branch cut here. So I guess like maybe a more precise way of saying this, I mean not necessarily precise, but one way of explaining this is as long as you make this gamma right and gamma left close enough to real axis, this is going to be approximately integral from epsilon to r of square root of x over x squared plus 1 dx, where this is just the real integral. And the key thing I'm using here is that when I'm looking at points in the first quadrant, right? So the values on the gamma right here, and I look at the absolute value of z, the angle here is going to be around 0 because I'm looking at the points that lie on this gamma right, so the angle theta is around 0. So this theta is around 0, so you get just the usual real square root of x. On the other hand, I had to emphasize this because this is not trivial. I mean, it really depends on the branch cut. And on the other hand, if I look at the gamma left of square root of z over z squared plus 1 dz, what's happening here is, I mean, first of all, I'm moving from r to epsilon in a backwards motion. But not only that, when I look at the points in the fourth quadrant where I'm actually moving along gamma left, my angle is around 2 pi. It's slightly less than 2 pi, right? So when I take the square root of z, what we are going to get is actually 2 pi in this data here. So you actually get e to the I pi, which is minus 1. So you actually have minus square root of x because of that. This is a key thing to observe, times x squared plus 1 dx. And I can reverse it back. I can reverse this back and change the sign negative to plus. So because of this, magically we actually get that this integral and this integral, really in the limiting case that I'm moving this gamma right on top of the real line, gamma left on top of the real line, we actually get the same integral for both. So essentially what is happening here? So if you call this main integral that we care about, so this is what we want to find, it is equal to I. In the limiting case where we're moving these to the real axis, you let epsilon go to 0, you let r blow up to infinity. What is essentially happening here is we have this like gamma contour of like square root of z over z squared plus 1 dz. This is really equal to integral on gamma left plus integral on gamma right plus integral on gamma epsilon plus integral on gamma r, and these two parts are approaching I. So this is approaching I, this is approaching, sorry, this is gamma, this is approaching I. So it's approaching 2I on this side. So then I is the integral that we want to find. So now let's think about what the rest of the things are going to turn out to be. So first, what about gamma epsilon? So when I look at integral of gamma epsilon of square root of z over z squared plus 1 dz, the thing to realize here is we are near 0 here, right? We're very near 0, especially as epsilon goes to 0. So when I take the absolute value here up to constant multiple, what is happening? Well, the length of this arc, this is length of this gamma epsilon is like, this is the circumference of a circle. This is like 2 pi epsilon, right? So this is epsilon. And what about the magnitude of this? In magnitude, I mean, if you're talking about magnitude, like this branch cut part really doesn't matter. It's just the usual positive square root of the modulus. So in magnitude, we're going to get like square root of epsilon over epsilon squared plus 1. And this is going to 0 as epsilon goes to 0. So this part is going to go to 0. And what about finally, what about the gamma r part? Well, now you're near infinity. So you have this thing, and here I'm really near infinity in the sense r is blowing up to infinity. And again, using the same sort of argument, this is r times square root of r over r squared plus 1. And as r blows up, this again goes to 0 because you only have r to the 3/2 power on the top. So this goes to 0, this goes to 0. So once we figure out what this thing is and what is this thing, you're integrating along this full contour. And here, like, the key thing is you have a pole, right? You're dividing by x squared plus 1. So to factor this, you have square root of z over z plus I times z minus I. So you have a pole So when, one way to think about it is near z equals to I, you have square root of I, which is like roughly a constant. So near z equals to I, you get roughly square root of I on top. And in the bottom, you have the behavior that looks like 1 over z minus I times like 2I, right? So, and 1 over z minus I, that's a simple pole of order 1 happening there. So you have a pole here at z equals to I, and you have another pole here at z equals to minus I. So you can evaluate this using the residue theorem. So we're almost done. Let's actually calculate that. So let's first think about what is the residue at z equals to I of square root of z over, again, z plus I times z minus I. And let's consider this entire function to be f of z, right? And what is a residue at z equals to I? Well, f of z looks something like this. Well, when I when I do the Laurent series expansion at z equals to I, so when I do at z equals to I, you must get something like this. C minus I to minus 1 times a minus 1, which is the residue, plus a naught plus c minus I times a1, and so on. You might ask, why do we not have term like c minus I to minus 2a minus 2? If we had terms like this, then when I multiply our function by c minus I, if we had a term like this, then when I multiply by c minus I still have c minus I to like say minus first power, and that's gonna make this function blow up when z approaches I, right? So again, if we had c minus I to negative second power, then when I multiply f of z by c minus I, then when z approaches I, you should still have a pole, you should still blow up. But when I multiply by z minus I to this function, then this disappears, and then this thing is well behaved at z equals to I, it's well defined. So we don't have that behavior, so we don't have this a to the minus second or more negative terms. So we know it's a simple pole, it's z minus I to minus 1, a minus 1, and really we just want to find, so the question is, how do you find a minus 1? And since this is a simple pole, there's an easy trick here, and that's to realize when I multiply both sides by c minus I to c minus I, in fact, then you get f of z is equal to a minus 1 plus a naught c minus I plus a1 c minus I squared, and so on. So when I multiply by c minus I, and then you take the limit, let's say I take the limit as z approaches I, then on the right-hand side, we're going to get a minus 1, which is exactly the residue. The left-hand side, I just have this limit, c minus I times f of z. So if it's a simple pole like this, where you just have minus first, you start with the negative first power, then all you have to do is multiply by z minus that point, and then like take the limit, and that'll get you what you want. So let's use that trick. So let's use that trick here. So residue at z equals to I of this is going to be the limit as z approaches I of square root of z over z plus I, and that's exactly going to be square root of I over 2I, right? And to find the square root of I, we have to recall how we pick the branch cut once again. So when you evaluate square root of I, this is e to the pi over 2I, right? I is equal to e to the pi over 2I. So again, I'm picking data such that this thing is between 0 and 2 pi. So your final output is going to be e to the pi over 4i according to this branch we picked. So this is exactly e to the pi over 4i divided by 2i. And you can do the other residue calculation in basically the same way. This is going to be the limit as z approaches minus I of square root of z over z minus I in this case, right? So this is square root of minus I divided by minus 2i. And this is e to the, so minus I is e to the 3 pi over 2i, right? So this is 3 pi over 4i now, divided by minus 2i. So to wrap everything up, what we get here is you have 2i here, this goes to 0, this goes to 0, and this thing is 2 pi I times the residue. So we get 2i is equal to 2 pi I times the sum of the residue by the residue theorem, and that's e to the pi over 4i over 2i minus e to the 3 pi over 4i over 2i. Now here, we can simplify it a bit. 2 cancels out, I cancels out, and I leave it up to you to think about this, but this is exactly cosine of pi over 4. This is exactly cosine of pi over 4. So we in fact get I is equal to pi times square root of 2 over 2. So that's really nice calculation, I think, that shows that, again, like this sort of party trick where when for certain integrals, we can actually evaluate it in the complex plane. Now there are just a few more quick topics that I at least want to mention before we wrap it up. And one of them is an argument principle. And in order to present this, I think there's a nice intuition, I think, from Ahlfors, if I remember, that if you look at integral 1 over 2 pi I over gamma of 1 over z minus z naught dz, then if you recall, like this was really the winding number. This captures how many times gamma is winding around z naught, right? Another way to think about this is now that we have some intuition on the logarithm, this is really 1 over 2 pi I times what is integral 1 over z minus z naught? Again, this is just a heuristic. This is natural log of the absolute value of z minus z naught, and then you have I times the argument of z minus z naught. And again, if you want to be naive and you want to use the fundamental theorem, so let's draw a picture here. So let's say you have z naught, and gamma looks something like this. Maybe you're rotating twice around. So this is what gamma looks like. And let's say let's call this point. Let's say this is the start point, and it's a loop, so it's also the end point. So you start here, you rotate twice, and you get to the end point. And if you want to invoke the fundamental theorem just very naively in an informal way, then you're integrating from start point to the end point here. And this part is, this is just well defined. At the start point and end point, this is going to be the same. So the difference when I apply the fundamental theorem, this part is just gonna go away. Really, the interesting part is the argument. Argument is really the angle. And when I accumulate, when I just keep track of what angle I'm increasing or I'm gaining as you rotate around, this is in this particular example, it's going to be like 4 pi, right? You're rotating like 2 pi, then another 2 pi. So this exactly gets you 2. So this is one intuition for like why, like again, this integral captures the winding number. And you can make a similar argument, say like to another integral that we're going to look at, which is integral of f prime of z divided by f of z dz. Like intuitively here, the antiderivative was natural log of z minus z naught. Here, the antiderivative that you should think about, again, this is not holomorphic on all of C or anything like that due to the same sort of issue. But here the antiderivative, you should think about it as log of f of c. When you differentiate this naively, you in fact get this. And again, if you try to make the same sort of argument, you get 1 over 2 pi I times, again, log of f of c plus I times argument of f of c as I'm rotating from start to the end. And again, this part doesn't really matter. And when you look at the argument from start to the end, what this is really capturing is how many times when I start with some gamma, and then I apply f to it, and I look at the image of the gamma under this mapping in the output space, I'm looking at like how much the argument is changing. So how much like additional rotation this f is in some sense giving to this gamma is actually mattering now. Like for example, maybe gamma looks something like this. It is going around just exactly once. But after you apply f, maybe f is like something like z squared, where now when I apply f, now the gamma is going to wrap around twice. So now it's going to capture things like this. And in fact, when you're near 0 or near a pole, what does f look like? Well, near a 0 or near a pole, we know, like, you recall from the Riemann surface sort of argument, f really looks like z mapping to z to the nth power, z mapping to z to the nth power. So here, n can be any integer now, in fact. And at a 0, you're going to look like something like z maps to z to some positive number. So you're going to contribute like say 3, whereas at a pole, so like for example, like if you have 1 over z, then rotation like this now in the output space is going to look like the rotation in the opposite direction, right? Again, 1 over z is meromorphic, it's not holomorphic at 0. So now this argument part is, for example, going to change by like minus 2 pi. So this heuristic argument is going to contribute 1 over 2 pi I times minus 2 pi I, so minus 1. So the crux of the heuristic thing here is that when you evaluate this integral, the zeros, say like order 3, like c cubed, is going to contribute plus 3 in this output, whereas zeros of order or pole of order, say n, is going to contribute minus n. So what this is going to turn out to be is this is just going to be the number of zeros minus number of poles like counting multiplicity. So if it's like a double zero, then you count it twice. And this fact is called the argument principle. That this integral is really just capturing the number of zeros minus number of poles, which is like really pretty argument, I think. It's possible that I also got this from Needham. Again, it's been some time, so all of these, so no promise my memory is fully accurate, but hopefully it's close enough. The next thing I want to mention is what's called the Rouché's theorem. And how this works is as follows. Say you have a meromorphic function f of z, and you have another f of z plus g of z. And here the setup is we have some gamma that you're rotating about, and what we have is on gamma. So on gamma, so this is like a bit of a weak condition, or weaker condition than requiring it on like on the entirety of inside of gamma. Just on the path, on gamma, let's assume g of z, assume absolute value of g of z strictly less than absolute value of f of z. So if you have this setup, it turns out, so this is the claim. This is a claim, and this is the Rouché's theorem. So let me actually write theorem. It's that f of z and f of z plus g of z, have the same quantity, number of zeros, minus number of poles inside gamma. So if it's like if everything is holomorphic, for example, then adding this g of z that is quite small on the boundary with respect to f of z cannot perturb the number of zeros. Number of zeros stays the same, for example, inside gamma. And I think I'm fairly sure this is from Needham. I think a beautiful heuristic here is when you can imagine something like this. Let's say the point you're rotating about is 0 here, and then imagine the Earth. So this is the Earth. And let's call the distance from 0 to Earth. Let's consider this f of z. So think of being 0 as the sun, I guess. And you also have the moon. We also have the moon here. That's not as easy to see as I like. Maybe here. So this is a moon, and the distance from Earth to the moon, let's call this g of z, is smaller than the distance from the Earth to the sun, f of z. So that's exactly the setup. And then your gamma is something like this, right? This is your gamma that you're rotating about here. And essentially, the reason this theorem is true, the heuristic proof of this, is the number of times Earth rotates. So if the Earth rotates around the sun n times, then the moon can rotate around the Earth as much as it wants. But from the point of view of the sun, and sun is only checking like this arc, right? It's only looking at the moon and seeing how many times is the moon rotating about itself, about the sun. Well, I mean, because the g of z is so short, as the Earth is rotating around, n times, the moon is also, from the point of view of the sun, going to rotate around n times. So this is the key intuition. The moon also rotates n times. And I guess a key thing to realize is if this is f of z and this is g of z, then f of z plus g of z is exactly this, right? F of z plus g of z. And since all of these arguments are consistent for f of z and f of z plus g of z, then essentially the argument principle, informally speaking, implies exactly what we want. So that's a Rouché's theorem. The very last thing I want to talk about, we're almost done, are some basic facts about conformal mapping. And actually, rather than doing conformal mapping, let's focus on what's most suitable for a first semester class in complex analysis. So let's talk about some basic facts on Möbius transformation. So Möbius transformation are maps that look like Z mapping to AZ plus B over CZ plus D. I mean, if you want to make sure this is non-degenerate, I think you usually check like AD minus BC being not equal to 0, like there's some determinant condition. But this is a map from CP1 to CP1 that is holomorphic. Like, I mean, you might argue that maybe the denominator blows up, but I mean, you can map to infinity, and because everything is linear on top and bottom, like everything works out. And some of the facts I want to mention about Möbius transformation. So the first thing is that it has 3 degrees of freedom. And what I mean by this is once I tell you where 0 maps to, so let's say I want to map 0 to like some C0, and I want to map 1 to some C1, and I want to map, say, infinity to some C2. Once I specify where like 3 points go, there exists unique there exists unique Möbius transformation. By uniqueness, I mean like modulo, like maybe like scaling A, B, C, D all by like 2 or something like that, some constant multiple. But modulo all that, there exists unique Möbius transformation satisfying this. So as soon as I specify where 3 points go, there exists one and only one Möbius transformation corresponding to that. The second thing is the Möbius transformation takes circles to circles in CP1. So in CP1, I guess one thing to realize is that a line in C, so if you have a line, so this is a line in C, from the point of view of CP1, a line is going to also be a circle. It's going to be a circle that wraps around like infinity in this case. So here you're heading towards infinity in both directions, right? So when I say a circle, I really mean a circular line from the point of view of the complex plane. So you're going to have circle to circle. And the final thing I want to mention is there is a pretty special Möbius transformation that maps the half plane to unit disk. So again, this is absolute value of Z less than 1. And by half plane, what I mean is imaginary part of Z greater than 0. So I'm talking about this part right here. This is the half plane. And there is a Möbius transformation that maps this to just the unit disk. And I think this is Z mapping to Z plus I over Z minus I. You can check this by plugging in some points. I guess like a force fact that I sneak in. I think this is slightly hard to prove. I cannot quite remember, but I think in one of the classes I've taken, I've seen a proof, where it does mention the proof that the Möbius transformation should take boundary to boundary. So what you can do is you can try plugging in like some numbers like 0, 1, 2, and you can see where those numbers go, and it should be on the unit disk. And because a line should map to a line or a circle, that should basically make it clear that the upper half plane needs to map to a disk. So that's one way to check. And I guess one nice trick that I want to mention, since I mentioned these three facts, combining all of this, is a standard like PhD level qualifying exam sort of question where you might be asked if you have a crescent. So by crescent I mean this is a circular arc, this is another circular arc. So you have a crescent like this. You might be asked how do you map this interior of a crescent to a unit disk? Using like a biholomorphic mapping that's like conformal. You can use Möbius transformation, for example. Like if you want to give an explicit map that's biholomorphic from interior of a crescent to unit disk, what do you do? And a really beautiful trick for this is, I mean, let's consider this point A, let's consider this point B, and pick any point on this arc, and let's call this C. What you can do is first come up with a Möbius transformation. That sends A to 0 and B to infinity. And this is easy. Just consider Z minus A over Z minus B, right? And in this case, because A is going to 0, so what does this do? So when I map it by Z minus A over Z minus B, you're going to, in the complex plane, B is going off to infinity, right? Whereas A went to 0. C, plug it C in here, and that's going to tell you where C went. Let's say C went here. This infinity can be anywhere, right? Like it's just infinitely far away. So what that tells you is that this arc that goes from A to B, the circular arc, because circle goes to circle or a line, in this case, in this sphere line, since one point went to infinity, really went to this ray. So the C minus A over C minus B maps this arc to a ray, and by the same reasoning, just pick some D here and check where D went. The other circular arc also went to some ray, right? Something like this. And now what you can do, because the interior here now got mapped to interior here, now what you can do is you just rotate. And you can rotate it to something like this, right? So now this ray looks like this, and this ray agrees with the positive x-axis. And now what you can do is you can just raise it to appropriate power. So raise to some power. Raise to appropriate power. when you raise this to some power, the real axis part is going to stay the same if you raise to positive power, whereas like the angle is going to increase by the multiplicative factor. So that's going to allow you to get the upper half plane. And once you get the upper half plane, then you can map it to a disk. I think this is a really pretty trick that I think I learned from some PhD student, I think, at some point. So I think that's everything. So there was a lot here. That's everything I did want to talk about in today's lecture. I mean, I'd be very willing to do something similar for, say, the point set and covering space and fundamental groups or linear algebra or abstract algebra. I'd be willing to. Obviously, this takes tremendous amount of time, so no promise I can get to it quickly. But I hope you got something out of this. Let me just quickly write a thank you here, since this is one of the longest video, if not the longest, I'm probably going to post on the channel. So if you actually stayed through the entire thing, thank you for watching. And again, I hope this gives you some insight to what first semester complex analysis class looks like. And if you've taken first semester complex analysis before, I hope this was a nice review. Hopefully you got more intuitions out of this as well.